In today's lesson, we're going to learn all about acceleration. Now, acceleration is slightly different than velocity, which is something that we've talked about in a previous lesson. Now, acceleration, I'll give you a quick example here. Some of you guys might recognize this clip from the show The Office.
Yeah, that's the safest part of a car. In the event of a crash, the driver always protects his side first.
Seriously? You're gonna sit in the back?
All right, so not sure if you're able to hear that, but you guys may notice when you're driving in a car, right, you're as a passenger. Now, most of the time, let's say if you have a bottle of water or even a glass, right, for the most part, it's not too difficult to drink out of it or just kind of, do your normal thing. However, you do typically notice when there is a massive shift in velocity, right, or a massive change. Again, some of you guys, if you've ever been in a car with a bad driver, or you yourself may not necessarily be the best driver, you think about how does your body feel when the person hits the gas too hard, right, too quickly, right? What happens when you just barely miss rear-ending another car in front of you, right? So you stomp on the brake really quickly, right? What's your body do? Also, especially if you've been in the back seat before, what happens when the driver takes a really sharp turn, right? What happens to your body? What happens if they take another sharp turn, but in the other direction? What happens to your body then? So, acceleration is going to be an example of all of these because acceleration is all about changing your velocity, changing your speed. That's what we're going to kind of look at here. So what I have for you guys on paper are some guided notes. So as I kind of go through this, again, on the paper, there should be a link to both this video as well as a link just directly to this PowerPoint in case you rather just kind of, follow along and do it yourself, or if you rather hear my voice. Either way, when we're talking about the difference between velocity and acceleration, velocity is going to be changing your position over time, or just changing your distance over time, right? Anytime you're moving, you have a speed. Most of you guys, when you're walking from point A to point B, have a constant velocity, right? That speed doesn't change. If you ever go on a really long road trip and there's just like a flat stretch of highway, a lot of cars have a button called cruise control, which just automatically will keep your speed at the same velocity, right? It won't change, won't speed up, won't slow down. It's an easy way to avoid getting a ticket. So that's velocity. However, when we change your velocity, right, you're driving and then you come to a stop sign and you stop. Or, you're at a red light and it turns green. Or, even better example is you are, doing your driving test or you're just learning how to drive for the first time and it's your first time trying to merge onto the highway, right? You try to figure out how much should you accelerate. Are you, stomping on the gas and trying to get up to the speed limit really, really, really fast? Or are you going a little bit slower and just hoping someone lets you in, right? So acceleration is just going to be that change in velocity. So you can think about some examples. So there's 3 different types of acceleration. I've kind of mentioned them already, right? But you can obviously write these in. We have any time that you're speeding up, right? Think about what the change in your body is, right? You're speeding up. Maybe you're in a roller coaster, right? You're at the very tippy top of said roller coaster, right? And then now you're going down really fast. Think about what's happening to your body. So speeding up is going to be a common form of acceleration. Slowing down is another type of change in velocity, right? And also changing your direction is going to be another form of acceleration. Now, funny story. One summer, I was hired as a driving instructor. However, I was pretty quickly fired, right? And when I went in there, I was asking, I was like, oh, what happened? It's like, I'm very qualified. I have, a teaching degree. I am a physics teacher, so I know all about motion. Obviously, I have a clean driving record. What's going on? And they said, well, we noticed that you try to incorporate too many physics vocabulary into your driving, and it's really confusing our students. They keep failing their driving tests. And I said, I have no idea what you mean. I call everything by the correct physical term. I'm sad that I'm not here for all the laughing that is sure to be had in the classroom right now. Moving on. All right, quick little example here. Obviously, you can pause the video and try this out. What you'll notice on this graph is we have time on the X and velocity on the Y. Take a look at these two cars, right? Think about which type of car would you rather own, right? If someone was offering you these two cars for free, right? Don't have to worry about gas or insurance or anything like that, right? Just like a no strings attached. Which one would you rather have? Now, think about cars. Most cars, I should say. Most cars that are, legal to be on the road. They can all reach the speed limit, no matter what the speed limit is, right? Whether it's, here and the speed limit is 60 miles per hour, or it's Los Angeles and the speed limit is 75 or 80 miles per hour. Anyways, they can all reach it in the same. So why does the type of car you have matter? If you ever, seen a video on YouTube or a commercial about a sports car, one thing that they'll typically talk about is not just how fast the car is, but how quickly it can reach those speeds, right? You'll hear a lot of, we can go 0 to 60 in 2.8 seconds, 0 to 60 in 2.6 seconds, right? That's how they're measuring the performance of the car, not just how fast it can go, but how quickly they can get to those speeds. Because I'll bet you, that a semi truck that is going downhill right through the mountain pass can, very quickly reach really high speeds, although they may not survive. Anyways, what you see here is that we have a change in velocity. Both cars are going to start at 0. And then both cars are going to reach a velocity of 30, in this case 30 meters per second. The big question is, which car is going to get to that speed first? You can try graphing this out. All right, so we have our first car, 0 to 30 in 10 seconds. So I know where my 30 is, I know where my 10 is. Right. This should be a little more linear. Let me try it on here. All right, so I have one car. I'm going to color code these a little bit better. So my one car can go 0 to 30 in about 10 seconds. Whereas this red sports car also can go that same speed, but in about 2.5 seconds. All right, so notice, once again, both cars are reaching that same speed, but one is reaching it pretty significantly faster than the other. Right? So again, if you're driving in, this little, Miata or, Ford Pinto or whatever it is, it's not exactly the most thrilling ride, but if you're in the sports car, right, you're probably either very scared or you're having a good time. All right. So now, what we can see here is we end up with another linear line, just like we had talked about in a previous lesson. The difference here is what's increasing is velocity versus time. We talked about before, our slope is going to be, right, what's rising divided by what's running. So in this case, we have velocity let me write this in here. Right? We have velocity is our rise, and time is our run. So when we find the slope, right, we're going to get acceleration. So, two different types of lines, right? If it's a displacement time graph or a distance time graph, right, same thing. Right, so you have a graph that looks like this, right, with this being distance, this being time, right? Our slope is going to give us the velocity, right? So this would be a fast car, right? And this would be a slow car. Whereas if we have a velocity time graph, I'm just going to do a V for velocity and a T for time. Right. In this case, what's a good way to say this? I mean, you could say both fast and slow, although you could have some fast moving objects that don't accelerate very quickly. I don't know. We'll say speeds up quickly. Speeds up slowly. Now, the reason why I bring this up, right, that your acceleration does not exactly equal your velocity. We talked about Usain Bolt before. He was a famous sprinter who set a lot of world records. One reason that he was a world-breaking sprinter is that he was actually way above average in height for sprinters. I think he was like 6'4" or 6'6", right? He had really long legs. Now, normally, having long legs is a disadvantage in sprinting, right? Because those with shorter legs, they're able to take many more strides, right? Many more steps per second, right? Every time you're stepping, you're pushing yourself forward. So someone with really long legs is not taking as many steps, not really pushing themselves forward as much. So in the first like second or couple seconds of every race, Usain Bolt would actually be, in the middle of the pack or close to last because he had a pretty slow acceleration. But he would get faster and faster and faster and faster over time. All right. A couple things here, right? We talked about motion maps before, right? Thinking about where the object is at every second. So let's say we have a person, or it could be a car, right? At 0 seconds, they're here. At 1 second, they're here. At 2 seconds, they're here. At 3 seconds, we're here. At 4 seconds, etc. 5 seconds, notice a big shift. So you notice in the first 3 seconds, they're really not moving all that much, right? Their position, their distance has not changed significantly. But after 4 or 5 seconds, right, it's changed pretty significantly. I'll pause here so you guys can try and make an estimation for what you think these two graphs should look like. So again, just kind of fill this in. Hopefully you guys are filling it along as you kind of go with the video. Right. So obviously the slope of the displacement time graph gives us velocity. The slope velocity time graph gives us acceleration. Now, in a case like this, we see displacement time, right? In the first few seconds, they're not moving all that much, but then over time, right after 4 seconds, right, they move really far, right? So we kind of get a line that looks like this, right? In those first few seconds, not a lot of change in their distance, right? And then progressively, right, their distance begins increasing more and more and more. And then particularly in those last few seconds, right, it increases by a ton. Now, looking at it from a nurse perspective, if we think about velocity, right, it kind of looks like at the beginning that they're not really moving all that much, right? They're starting from 0, right, velocity of 0, and they're getting faster and faster and faster and faster. So you think back to the idea of a speedometer, right? The thing that tells you your speed in a car. right? With it being like 10, 20, 30, 40, 50, 60, etc. Right? If we're thinking about like your speedometer as you're speeding up, think about you're at a red light, you press on the gas pedal, and you are slowly pressing it, right? You're kind of increasing it slowly, right? Basically at a constant rate. You'll notice that your speed doesn't just go, right? You'll kind of slowly progress like this, right? The little speedometer dial is not at any point like just like jerking forwards, right? It's going to have a steady increase as you're speeding up. Assuming you're not like herky-jerky on the gas pedal. So we should see here is we should see, right, a velocity starting at 0 and then progressively increasing at a steady rate. Right? So like let's say every second, right, you're increasing your velocity by 10 miles per hour. Right? At 1 second it's 10 miles per hour, at 2 seconds it's 20, at 3 seconds 30, at 4 seconds 40, 5 seconds 50, 6 seconds 60, right? That would be a linear increase, which is what we see here. All right. What about if we get the opposite? What if instead we have a case where in 1 second we travel a pretty good distance, right? But from 1 to 2 seconds, right, that distance decreases. From 2 to 3 seconds, that distance increases by a lot. You think about this as a person or a car or really any other physical object, right? What is the object doing in this particular case, right? Is it speeding up? Is it slowing down? Is it moving with a constant velocity? Again, I'll pause, or you should pause, so you guys can try and solve this on your own. All right, you know what it looks like when an object is speeding up. What might it look like when an object is slowing down? So let's say you're driving and then the light turns red, right? Yellow and then red, right? You slow down. You're still moving forward, right? That hasn't changed. Your distance is still increasing, right? You're getting closer and closer and closer to a stoplight, but what's happening to your speed or your change in distance, right? So we think about from 0 to 1 seconds, right? You've moved pretty far, right? We're just gonna show the difference here. Right, so like from 1 to 2 seconds, you've moved pretty far, right? From 2 to 3 seconds, what happened? And from 2 to 3 seconds, what's going on, right? So in each change in time, we're seeing that the distance is still increasing, but at a slower and slower rate until it's essentially horizontal. So similar thing with velocity, right? You think about what's going on with your speedometer. If you're driving, down the street or whatever, right? You're going at whatever the speed limit is, right? Let's say 40 miles per hour. And then as you get to, let's say 40 miles per hour, right? Up here. And then when you get to the stoplight, right? You're obviously, hopefully, going 0 miles per hour. So in the in-between time, your speed is decreasing at a linear rate. Now, unless you're a really bad driver and you go 40 miles per hour all the way until the last second and then you stomp on the brake and pull your e-brake, etc. Right? Hopefully that's none of you. So your speedometer might look like, right, starting at whatever the speed limit is, and then as you are pressing the gas, because you don't want to bang your head on the steering wheel, right, you are steadily pressing on the pressing on the brake. And so your speed is decreasing at a linear, steady rate, right? If it's kind of like doing this, right? You're just kind of like stomping on the brake, you'll feel it, right? Your body will feel it, your passengers will feel it, your stuff will fly over your car. You'll notice. All right. Now, we're going to do a little bit of problem solving here. When we're talking about acceleration, we have several different things that we're calculating. You have our displacement or distance. Instead of writing that every single time, we can use a symbol d to represent our change in distance. We also have what we would consider to be our initial velocity, right? What is our starting velocity? At 0 seconds, what is the velocity, right? Hence why we have the letter V and then the 0, right? Because we're trying to show at 0 seconds what is our velocity. And then, assuming that we're speeding up, slowing down, or change our velocity, at the end of the scenario, what is our final velocity? We use the letter A for acceleration and the letter T for time. Because we're talking about a change in velocity, the one way that we can calculate that change in velocity, a symbol we can use, is the Greek letter delta, which represents change. If we expand that out, right, change just means you're taking your final number and subtracting the initial number. You know, for example, if you want to know your change in height in high school, you would take your height on the day that you graduate minus the first day of freshman year, right? You always start with the final and then subtract the initial. If we replace all the words with our symbols, we get a much more manageable formula. All right, this is a formula that will be a lot easier to write and a lot quicker. All right, so for this first problem here, we're asked what's the acceleration of a car when it's moving from 15 meters per second to 35 in 10 seconds. Now I'm just going to solve it out on here. So again, on here, right, d is our displacement, VO, our velocity at 0, right, final velocity, acceleration, time. Right, so in words, right, final velocity minus initial divided by time, right, our symbols are going to be, right, our symbol for acceleration is A, our symbol for final velocity is just V, for initial velocity, VO, divided by T. You can fill in the units, right? So in this case, what we're going to do is when we're solving a problem like this, we can highlight the things that we're given and then solve for the things that we're trying to find out. So in this case, we're given 3 numbers, and we're trying to solve for the last. So one thing that's helpful in all these cases is using our formula and filling out a chart. A chart is going to help us kind of put in order what each variable is. So first off, right, we're given a time. We're given a initial velocity. Again, it helps to read the story because physics is all about making sense. We're given a final velocity, and then we're trying to find our acceleration, which we don't know. So I can fill these in, right? In this case, we have a car that's starting with a velocity of 15 meters per second, right? So it's not at 0. It speeds up to 35. Right? Let's say, I don't know, someone cut you off and you're trying to catch up to them to see who's driving that car. All right, so you increase your speed. I wouldn't do that because that sounds very unsafe. Let's say you do this over a period of 10 seconds. Right, so you essentially are increasing your speed by 20 meters per second in 10 seconds. Notice I kind of just did some mental math there, but you'll see how this works out with our formula. So our formula is going to be acceleration, which is conveniently what we're trying to find out, equals velocity minus initial velocity divided by time. Now we actually know all of these numbers with the exception of acceleration, right? We know the final velocity, right? That's how fast you're going at the end. It's 35. We know how fast you're going in the beginning, which was 15. And then we know how long it took them, which was 10 seconds. So we end up with acceleration of 20, right? That's a change in velocity, right? They increased their speed by 20 meters per second, and they did so in 10 seconds. Conveniently, this is some pretty easy numbers to work out. So we end up with a velocity of 2. Now the units in these cases are going to be measured in meters per second squared. What I mean by that is every second you're increasing your velocity. So you're basically increasing your meters per second per meters per second. Really what that means is if we look at our units, right, the A is going to be meters per second, which is our unit for velocity, minus meters per second, which is again our unit for velocity, divided by seconds. So what we end up with meters per second per second. So another way to write that is meters per second squared. It's a little bit easier than writing meters per second per second. All right, moving on. One more here. Again, you can try to figure this out on your own. Just know that acceleration can be negative. It doesn't mean that your object is moving backwards. Simply means that that is where the acceleration is. So if you think about it this way, in this first problem, right, our object was speeding up, right, and we got acceleration that's positive, right? They're getting faster. So what might it look like if an object is getting slower, like in this case? So once again, we'll kind of define what we got here. So first off, we have a train that's slowing down. So immediately we already know what the motion is like, right? It's slowing down. Easy. So it's slowing down from 12 meters per second. So that means that's where it's starting, right? That's its speed at the beginning, right? The initial velocity doesn't mean that the speed is 0. It just means that that's whatever the speed is at 0 seconds. So when the story starts, they're moving 12 meters per second. We're also given the time, right, in 8 seconds. And we're trying to find the acceleration, which we don't know. But you notice it only gives us 2 numbers. So again, this is where we have to use our brains, because physics is supposed to make sense in the real world. What this is telling us is that this train is slowing down, and eventually it slows down to a complete stop. So you think about if an object is moving at a complete stop, does that represent a number? Can we represent that with a number? We can. Okay? That would be 0 meters per second. So, just like we did before, we can plug all this into our formula. End up with our final velocity, which is 0 minus 12 divided by 8. So notice we're going to be subtracting 0 by 12. So the answer is not going to be 12. All right, we're starting at 0 and subtracting 12. So if you have $0 and then you owe $12, right, how much money do you have? Not a lot is the answer. So we're going to end up with here, I'm actually going to end up with a negative number, right? Because I essentially have negative 12 divided by 8. I end up with negative 1.5 meters per second squared. So that means every second our velocity is decreasing, right? It's changing. In this case, it's changing in the negative direction, right? My speedometer is starting at, in this case, 12, right? And then moving down towards 0. And if I move down towards 0 at a rate of 1.5 meters per second every second. All right, finally, here we have what's called a stroboscopic photo. So it's basically if you set up a dark room and then you set up a camera where it will flash every unit of time and kind of take a picture of that object as it moves, right? And then kind of overlay all these objects together in one image, right? Kind of shows us how it's moving. So what you can do here is think about really any object that's thrown up in the air. Right? In this case, it's sort of up in the air and it bounces. So think about at what point in this arc is it moving the fastest? And at what point is it moving the slowest? So you can pause the video here. And I'll just kind of give my answer key. Just gonna go through this. Okay, so you can obviously see kind of where they're all bunched up. Right, kind of like our motion maps up here. Right, all bunched up. Obviously, it's not moving very quickly. So one place where it's moving the slowest. I'm circling both. Black on black is not helpful. All right, this is slow. Right, you think about any object that you throw up in the air. As it reaches its peak, before it changes direction and starts falling down, right, it gets slower and slower and slower, which obviously means that when it reaches its highest height or highest peak, its velocity for a split second is actually 0, right, because it's been slowing down all the way to 0, and then it actually changes direction and begins to speed up. So as it speeds up, right, it's going to get faster and faster and faster and faster. You can see in this image, right, as they get further and further and further apart, right, they're gaining more of this movement energy. So accelerating and speeding up. All right, obviously if we were to kind of continue this image, right, what we would eventually see is we'd see something like this, right, and then it would just kind of continue. Now, obviously, if it kept bouncing, it would get lower and lower each time because it would be losing some of the energy as it collides with the ground. All right, so that is the end and conclusion of this lesson. Again, sorry I've not been at school. I'm not having a fun time. But I'll see you guys soon, and we'll kind of pick up where we left off and do our next lab, which should be an acceleration lab. So you can get ready for that.